I want to have a look today at logarithms. Logarithms, when I started using them many years ago, were all based on log tables, and we didn't have any calculators, and we had to use logarithms as a means of doing sums of all types. They're still widely used, however, in the fields of physics, chemistry, biology, engineering, and the idea of logarithms is that it can make some calculations very much easier. So with the invention of calculators, why do logarithms still matter? Why are basically logarithms important? Well, to understand that, let's go and have a look at basically indices, exponents and that lot, and see if we can follow this through and why we need to use logarithms. Let's have a look. Now, if I just zoom in, we're going to have a look at some things about logarithms. So let's say I've got a number and I say we're going to do, just zoom in a bit more, there we are, 2 to the 4, and we say that 2 to the 4 is going to equal 2 times 2 times 2 times 2, which is going to be 16. Right, so what have we got here? Well, we've got various bits and pieces. We call this one here the power, but also it's sometimes called an exponent or an exponential, and sometimes it's called an indice, or in this case, because we've only got one of them, an index. This number also does have a name, and we're going to use that name because we're going to play around with logarithms today, and so this is called the base. So we know various bits and pieces about all sorts of numbers, and we've played around with them. So we know perhaps 8 squared is going to be something like 64. We know that 8 to the power of 2, or 8 times 8, is going to equal 64. 8 is our base, 2 is the power, and 64 here is our answer. Now, why do we need to try and study logarithms? What's the point of trying to understand logarithms? Well, what we can use logarithms for is to try and help us later with our differentiation and our integration, and because we need to know those in a lot of detail, then we need to follow these rules on logarithms and what they are. So let's have a look at a simple sum. Let's take a sum where I want to do 2 to the power of 4, and I want to multiply this by 2 to the power of 3. Now we can do this very easily. We know that 2 to the power of 4 is 16, and we know that 2 to the power of 3 is 8, and I can simply multiply these together to get my answer. But we know that when we're playing around with these indices, that we could just say, well, this is the same as 2 to the power of 4 plus 2 to the power of 3, 4 plus 3, which gives us 2 to the power of 7. And I can easily work out that 2 to the power of 7 is going to be 128, which is what 16 times 8 is. Now, what have I done in this? Well, using the rules of indices, we know that when we want to multiply two indices together, we can add them up. Okay. If we want to do division, so let's suppose we want to do the reverse sum, 16 divided by 8, that would be the same as doing 2 to the 4, because that's 16, divided by 2 to the 3, which is 8. And when we get to our rules of indices, we know that when we divide, this is going to be 2 to the 4 minus 3, which is going to give me 2 to the 1, or we would normally write that just as 2. Using the rules of indices tells us that we subtract the powers to get our new power. Now, when we use the powers, we've changed basically a multiplication problem into an addition problem. When we've done a division problem, we've changed that into a subtraction problem. And this is why it was used historically, because these were invented by a couple of different people. There was a guy called John Napier, and he made Napierian logarithms, and he lived around about 1600. And a little bit later was another guy called Henry Briggs, who also developed logarithms as a way of trying to replace doing these difficult multiplications. They replaced these difficult multiplications simply because it was easier to add and subtract than trying to do multiplication or division. And it's stayed with us. So that's the idea about logarithms. So let's look at what is a logarithm. So we've got here our number 16, and we can say, well, that's going to be 2 to the power of 4. But I could write that differently. What I could do is I could take logs of this, and I can say log to the base 2 of 16 is 4. And this is sort of an interchangeable way of looking at the numbers. So there is our base, here is our answer, and here is our power. And this is how they work. Right, pencil repaired. Let's see if we can go on. So these two are equivalent statements. If you write this, you could have written that. And if you've written that, you could have written it the other way. They are the same. And so what you have to be able to do in A-level maths is that you've got to be able to convert one of these to the other, basically almost without thinking about it. So if I've got another number, and we'll choose 8 squared, and we know 8 squared is 64, 8 times 8, then we could write that as log to the base 8 here of 64 equals 2. So they are equivalents. We could try any other one. We could do it the other way. And we know that perhaps the log of 3 to the 27 equals 3. That's the same thing as writing 3 cubed equals 27. They are equivalent. And if I write powers, I could write logs, and if I write logs, I could write powers. And these are easy ways of converting from one to the other. What we need are some general rules when we play around with some of these. So if I replace some of these with letters, we can say that a number, a, the base, to the power of another number, n, is going to give me an answer, x. So I could rewrite that as log to the base a of x, and that equals n. And we just write these down, and you've got to be very comfortable with just converting one to the other. And what I normally would do with students now is give them lots of these and ask them to write them in the opposite form so that you can just do it. And at the beginning of a lesson I would often start by just writing down one of these, and they would write down the opposite for me. And they can do it then almost in their sleep. So let's start coming up with some rules of logs and see if we can follow some of those. So we've got this idea of writing an expression as a logarithm, or a logarithm as an expression, and then our next job is to have a look at other things. So let's look at something to the base 10. What do we know? Right, let's take 10 squared. Well, we all know that is going to be 10 times 10. 10 cubed, we're happy with that one. That's simply 10 times 10 times 10. So if we go down to 10 to the 1, yep, we know that is just the equivalent of writing 10. So let's take that number, 10 to the 1 equals 10, and let's write that one as a logarithm. Okay, so that's going to be log to the base 10 of 10 equals 1. And if we try that for any other number, 2 to the power of 1 equals 2. So I can say that the log to the base 2 of 2 equals 1. So we get a general rule. And the general rule is that the log of any base to that number is always 1. So this is a general rule that we need to follow. Now let's see if we can look at a few rules of logarithms, and they're not really very difficult to follow. Let's see what we know. Let's take a number. X equals a to some sort of power, and we'll take another number. Y equals a to some other power. This is trying to do this fairly generally. Now, how can I write this as a log? I can write this as log to the base a of x equals n. And this one we can write as log to the base base a. Let's get me rubber out. Log to the base a of y equals m. There we are. What do we know about trying to multiply x and y together? Well, that's easy. If I want x times y, then that would be the equivalent of saying a to the n times a to the m. And if I wanted to write that, I could write that as a to the n plus m. Now, I already know what some of these things are. So let's see. I know that n is log a to the x, and I know that m is log a to the y. So let's put that together. So if I were to take a log of both sides, so we can say that the log to the base a of xy would be here log to the base a of x plus log to the base a of y. So if I want to multiply any two logs together, then all I actually need to do is add them. And this is what we do when we try and play around with logs. Let's see if we can try one of these. So let's suppose I want to take the log, and I'm going to use log to the base 10 of a number. So we're going to multiply 2 by 3, and that's going to be by taking then the log to the base 10 of 2, and we're going to add that to log to the base 10 of 3. So let's get the calculator out and see if we can do this. And I've been having a few problems with the machine this morning, so we'll see how well it works, but if it doesn't, then it's not. Let's get just the calculator out. Right, so let's look at what is log, and it's log to the base 10 of 2, and I've got my number, and I'm just going to write that one down. This is going to be 0.3010, And what I'm going to do with this one is I'm simply going to store this in a memory. I'm going to store that in memory A. Let's look at the other one. We've got log to the base 10 of 3. So I've got log, trying to put this where you can see it, log to the base 10 of 3, and that's going to give me another number, 0.4771. And I'm going to put that in memory B, so I'm just going to store this in memory B. And what I'm going to do is now, rather than add those up, because it won't be very accurate, I had more decimal places, what I'm just going to do is I'm going to take memory A and I'm going to add that to memory B. Recall B, and that's going to give me an answer of 0.77815. We could have added those up manually. I wanted more decimal places, because what I'm now going to do is I'm going to convert this back to the other form. So I'm just going to do shift 10 to the power of my answer, and that will give me the answer 6. So we've there quickly demonstrated that we could use logarithms to work out a sum. 2 by 3, 6, or we could have gone through that laborious process and got the same answer. Now that seems like an awful lot of work to try and do something, but it's important. So our first rule of logarithms that you need to remember is that if you want to multiply two logarithms together, you simply need to add them and we get an answer. Let's suppose we've got something else. We want to now take another number. Let's suppose I want to do something like x to some sort of power. Let's call it d, and that would be some number a to the n to the m. There's just my idea here. Now, using the rules of indices, we know that if I want to work out my answer, x here, x, which may be to a power, is going to equal a to the n times m. If we want to think of that as logarithms, then what we can do is decide that if I want to take log to the base a of x, that's going to equal here n times m. But we know from other facts that we've just worked out that I can know that a number is just a log. And so what I can do is I can simply multiply one of these numbers by the log. So this is going to be m times the log to the base a of x. So any log to a particular power can be written as that number times this log. And we use this a lot. Let's suppose we have something else. X is here a to the n, and let's have y equals a to the m. Then we can write those as our logs again, and we remember that means it's going to be log to the base a of x equals n, and here log to the base a of y equals m. So let's now see if we could perhaps take a number x and divide it by y. With this system, that's going to be a to the n divided by a to the m, and we'd write that as a to the n minus m. Let's try and write this as logs. So let's take the log of x over y. Well, we already know what this is going to be. So this is going to be n minus m. And n, we know, is log a of x. So log of x over y is going to be the log of a to the x minus log a of y. And there's another rule that we need to be aware of. When we play around with some interesting things, we discover that there's an interesting little fact that really bugs a lot of students at GCSE, and we say that any number 2 to the power of 0, for instance, equals 1. We know that x to the power of 0 equals 1. And as I tell my students, even your name to the power of 0 will equal 1. Let's write this in the form of a logarithm. So if I've got a to the 0 equals 1, then we write that as a log, and we say that the log of a to the 1 equals 0. So the logarithm in any base is always going to be 0. Right. Now, what other things do we know about logarithms? Well, there's a rather interesting fact that we might be given some horrible sum to try and work out. Suppose you're asked to find log to the base 2 of 512. Now, what is that? So this is the same as being asked, what is 512 as a power of 2? Now, I know, because I've played with this many times, that log to the base 2 of 512 is 9. We could work that out on the calculator just as easily. If I'm asked what is log to the base 8 of 1 over 64, well, that's the same as saying what is 1 over 64 expressed as a power of 8. Now, I'm not very good with these numbers, so I could write this as log to the base 8 of 64 here to the minus 1. Oh, that's looking horrible, isn't it? Now, I know 64 to the 1. Well, let's just worry about 64 for a minute. 64 I also know is 8 squared. So if I replace the 64 by 8 squared to the minus 1, we know from indices that's the same as 8 squared times minus 1, and that gives me here 8 to the minus 2. So I know, using indices then, that log to the base 8 of 1 over 64 will equal minus 2. Right, well, let's see what we can try and do with this. Let's move on. Let's see if we can look at something like log to the base 5 of 25. We're being asked, what is 25 expressed as a power of 5? Now we know that 5 squared equals 25, so log 5 of 25 is 2. Now what would happen if someone asked me about this the other way round? What is the log of 25 to the 5? Now, looking at that the same way, I know that 5 here is the square root of 25. So I know that 25 to the half equals 5. So log to the 25 of 5 equals a half. So if I want to swap these two numbers round, what we do is we put them one over the other. So if I've got log to the b of a, it's the same as writing 1 over log of a to the b. This one students forget more than any other one, and sometimes it's really quite useful. The problem is they forget them simply because they've got a calculator, and they think because they've got a calculator they don't need to remember some of these logs, but in fact they become really useful. So if I want to write one of these out, we've simply got something like log to the base 8 of 2 would be the same as 1 over log to the base 2 of 8. So we can just write that one out very simply. When we come around play with logs, we notice on our calculator that there are two specific log buttons. We've got log here of any base to any number, and then we've got this one, ln, a different sort of log, and these are either natural logs or sometimes called Neperian logarithms. So when we meet these in maths, we meet log, and log generally is another way of saying log to the base 10 of some number, or we meet ln, and ln is here log to the base e, and we meet this funny symbol e. And then what is e? Well, e is one of these peculiar numbers that if I take a number and I differentiate it, I end up with the same number. It's called the exponential constant, and e, and it's equivalent in numbers to about 2.718. This number, very much like pi, goes on forever. It's a an infinite decimal expression. Now, why do we use this peculiar number? Well, we use base e because most physical systems, most biological systems, most chemical systems, and a lot of things like economic systems, they all are based on this e, this natural logarithm. Why do we use base 10? Well, the answer to that one is very simple. We've got 10 fingers, thumbs, so we tend to use and count in tens. But nature doesn't have those 10. There's no reason why it should. And so it uses some other basis for how it works. And those are these things based on e, the exponential constant. So, just as before, when we know that log of 10 to the 10 equals 1, I could write that as log just of 10 equals 1, and generally when we write log we're implying log to the base 10, and when I play around with ln we're talking about here of base e here so it's a similar sort of thing that we can play around with. So we can use logarithms to solve all types of awkward equations, and when we try to do some of this, it's sort of necessary to do some clever little tricks, and we'll have a look at some of those. This is really useful for when we're playing around with differentials, and when we start to play around with differentials we find that this log to the base e is invaluable. So log to the base e is really a useful thing that we can try and play around with, and it's a good idea to know it in detail, but we'll worry about that a bit later. Right, let's suppose we've got a sum to try and do, and someone says, okay, log to the base 3, log base 10 of 3 of x equals the log of 5. Using our rules of logarithms, I can say that x times log of 3 equals the log of 5. This is more straightforward because I can now divide both sides by the log of 3. So I now have a way of simply of working out what x is, and it's an easy way of trying to say that log x here is going to be the log of 5, which we can put in the calculator, divided by the log of 3, both to the base 10. So we can look that up really easily. Give another nasty problem. 3 to the x equals 5 to the x minus 2. We've got the unknown as a power, so I've got to try and do something with this, and this is where logs come in really usefully. So I've got 3 to the x equals 5 to the x minus 2. Okay, so let's take logs of both sides. So this is going to be log 3 to the x equals log 5 to the x minus 2. Now, using the rules of logs, I know that that's going to be x times log of 3, and this one is going to be x minus 2 times the log of 5. Better put that in brackets. And that we know from multiplying out the brackets here is going to be x log 5 minus 2 log 5, and that's going to equal that. Now let's get this sorted out, and I'm going to put the x's on one side and the other number on the other side. So if I take the x over that side, bring this over here, I've got 2 log 5 is going to be equal to here x log 5 minus x log 3. let's take a factor of x out. So x log 5 minus log 3. This is becoming easier now, and we know when we've got two logs, we could write that as x log.
I'm reminding you, take up written tablets.
Just dealt with my Alexa device. X of 5 divided by 3. And we can look that up in the calculator. Or we can rewrite this now to get what my x is, and my x is simply going to be now taking this back over to that side. We've got 2 log 5 divided by log of 5 over 3 equals x, and we've managed to work out how to solve a nasty equation. Last thing, and that is knowing something about something called an inverse operation. What do we know? Well, when we started, we knew various things. I know that perhaps a number like 8 is 2 to the power of 3. We can work out that that might be the same as the log of 2 to the 8 equals 3. We can use our simple ideas of playing around with this, that I can change some of these logs around to get inverse functions. So if I've got a function here which is something like the log of e to the power of x, I know that that's going to be x of the ln of e. We know that ln of e is going to equal 1. So we're stuck with x. So these, which are inverse functions, cancel each other out. And this becomes really useful when we're playing around with calculus, with integration and differentiation. So we've got a few ideas here. So we know that the ln of e to the x will equal x, and I know that if I've got e to the ln of x, that's also going to equal x, and this becomes really useful when we're playing around with solving differential equations. So I hope that's given an idea about logs, why you might try and use them. We can play around with a lot on logs, and it's a way of trying to solve many of the problems that we meet, especially in integration and differentiation. So we start off looking at logs as a topic, but generally where we actually use them is for solving differential equations. Hope that's given you some idea about logs and how they're useful. I'll see you next time, and we'll take a look at another subject that people find difficult in A-level maths. I'll see you then.